subscribe.
A single diode rectifier is enough? Really?
I mean, is it not?
No! A single diode rectifier is weak! You better not use them in high power applications. I mean, shouldn't you know all this stuff already? What are you, a mechanical engineer?
No, I dropped out.
You need a full bridge rectifier. Full bridge! I have an eye on you.
Alright then, so I guess we'll be using a full bridge rectifier. A full bridge rectifier consists of 4 diodes in this arrangement, and a diode allows current to flow through it in one direction but not in the other. With a single diode rectifier, when an AC signal is applied to the input of the rectifier during the positive duration of the cycle, nothing changes on the output. However, during the negative part of the cycle, the rectifier simply blocks current flow. Now, with a full bridge rectifier, during the negative duration of the cycle, the rectifier flips the signal so that the output voltage never drops below 0. So the first part of the circuit can be traced like so. Cool. Here we can add our secondary transformer with, just like the first one, a few turns on the primary and a lot more on the secondary. Now, if we were to connect the primary of the second transformer in series with the secondary of the first coil, this coil would simply act like a short circuit and the capacitor would never be able to charge up. And of course there would be absolutely no output on the secondary. This is why we need some sort of switch that would be open while the capacitor charges. Once the capacitor reaches a certain charge, therefore a certain voltage, the switch would close, allowing massive amounts of current to be instantly flowed through the primary, creating a high voltage pulse on the secondary. You'll notice that when the switch is closed, we have an inductor and a capacitor in parallel, just like before. This means that they will, again, pour charges into each other and oscillate at a certain frequency. And if we take a look at that pulse graph from the X26 taser, that is exactly what we see here. Anyway, the easiest way to create a high voltage switch is to simply have 2 conductors separated by an air gap. And that's it. And here's how they work. Every material has a dielectric strength measured in megavolts per meter. For instance, air has a dielectric strength of 1.5 to 3 megavolts per meter. That means that if we had 2 probes separated by 1 meter, we would need to apply 1.5 to 3 million volts for the insulation air provides to break down, ionize, and form an arc. This also means that if we wanted a switch that closed between 1.5 and 3 kilovolt, we could simply have 2 pieces of metal separated by 1 millimeter. And voila, we just created what's commonly known as a spark gap. And guess what? We're done. That's it. Well, in theory. Let's order the high voltage capacitors and high voltage diodes and see what we can do. And here they are. So after a little bit of soldering, here's what that looks like. So for the first test, I used a piece of wire to temporarily simulate the trigger transformer. I pumped 10 kilohertz at 2% duty cycle through the primary, and to my surprise, it seemed to work flawlessly. However, after listening to it for a while, I noticed something pretty annoying. The pulses seemed to happen at very random intervals. And to try and figure out why, I used a cheap $30 oscilloscope. This particular oscilloscope can only measure up to 50 volts, which is no good. To get a decent voltage measure, I'll be using an improvised 100-to-1 voltage divider. And yeah, this setup is definitely pretty dodgy and not very accurate, so I definitely wouldn't use this on a more expensive oscilloscope, which is why these cheap ones are so awesome. Right, so let's measure the voltage across the capacitor. And as you can see, the capacitor slowly charges up and instantly discharges. So that's exactly what we expect. However, you can see that the discharge voltage is indeed very imprecise. So why is this? Well, we saw earlier that the dielectric strength of air can vary between 1.5 and 3 kilovolt per millimeter, not a fixed value, so the air isn't the best material for this. So if only we could have some kind of spark gap encapsulated in a gas with a very precise dielectric strength. Oh wait, what's this behind your ear? A surge arrestor gas discharge tube? Pfft, perfect! These discharge tubes are usually used for high voltage circuit protection and should work flawlessly for our purpose. Okay, so let's replace the spark gap with the discharge tube and see what it does. Nice, much more precise, and the pulses are nice and evenly spaced out. Now let's move on to the dreaded high voltage trigger transformer. I wanted the output arc to be about 50 millimeters long. That means the transformer needs to have a peak output voltage of around 150 kilovolts. Probably a lot less than that, but this will make sure it's able to arc across that distance every single time. To maximize efficiency, we'll be using a ferrite core. I ordered a few of these ferrite rods used for crystal radios. I wound 10 turns of thick copper wire around it. Then I wound the necessary number of turns of much thinner copper wire around a piece of PVC pipe. The pipe will insulate the two coils, and once again, to my surprise, it worked flawlessly. But obviously, the issue here is that it isn't exactly compact. But before I even started to figure out a way to shrink this thing down, I wanted to spend some time optimizing the oscillator circuit, as at the moment it lacks in power and efficiency. I also realized something quite problematic. Remember how the input frequency signal needs to correspond to the resonant frequency of the inductor and the capacitor? Well, turns out the inductance of the coil significantly changes depending on how full the capacitor is. This means the circuit will only resonate when the capacitor is under a certain amount of charge, which significantly reduces overall efficiency. So, if only there was some kind of oscillation circuit that would automatically tune itself to the resonant frequency of the transformer. Well, of course, there are tons. In fact, here's the circuit used in the high voltage kit we looked at earlier. And as you can see, the transformer here has two primary coils, a power winding and a feedback winding. And in fact, a very similar circuit is used in the stun gun we looked at earlier and in bug zappers. However, the issue with these particular circuits is that they are very low power. A quick simulation in LT Spice shows that the current they deliver to the coil has a very short duty cycle. We could of course increase the input voltage, but that would just fry the transistor. Luckily, there exists another common circuit that uses two power MOSFETs and two resistors. Two Zener diodes are simply used to protect the gates of the MOSFETs from high voltage spikes. This time, the transformer has two power coils bridged together. And basically, when one MOSFET is on, the other one is off and vice versa. This will result in a magnetic flux flowing in one direction, then the other. This particular circuit was supposed to have a bit more oomph, so I assembled a quick prototype, gave the transformer 3 windings for each coil, and yeah, now we're talking. A quick check on the oscilloscope shows that both MOSFETs run at a whopping 40% duty cycle, which means that the entire board is basically constantly pulling an insane amount of current. Although this is a pretty scary looking arc, on its own it wouldn't actually be very effective against an attacker due to the high frequency. The arc is hot enough to melt copper though, and would work great as an instant sausage grill. But ultimately at this point all we have is a beefed up arc lighter. The issue with this particular circuit is that if I tried to run it on the 12-volt battery, the MOSFETs would just fry instantly. I tried a couple things. I tried adding a fat resistor to try and keep the current under control, but this is extremely inefficient as most of the power is being turned into heat. The best and easiest way I found was to simply power the circuit at a much lower voltage. 7.4 volts from this double cell 50C LiPo battery seems to be just right. At full charge, the circuit pulls an average current of around 13.5 amps. At 7.75 volts, that's 104 watts. And yeah, that's definitely a lot of juice. So when designing this thing, I had the choice between using a low capacitance or a high capacitance capacitor. A small capacitor would result in weaker pulses, but there would be a lot of them per second as less energy is required to charge them. Or I could go with a beefier capacitor and get fewer but much stronger pulses. And I decided to go with the latter. I decided to hook up 3 in parallel. This triples the capacitance. And by the way, don't even think about measuring the output power of a stun gun in volts. There's absolutely no way to predict how powerful a stun gun is solely based on its peak output voltage. Also, the voltage of a stun gun is actually limited by the length of the arc. Remember, the dielectric strength of air is 1.5 to 3 kilovolt per millimeter. So for instance, I'm guessing this particular model has no more than maybe 20 kilovolts across those probes, and 500 to 600 billion volts seems to be the trendy voltage claim at the moment, so yeah. If you plan on buying a stun gun, don't be fooled by these outrageous numbers, as they are completely meaningless, even if they were true. But once again, I digress, so let's move on. So I needed to figure out a way to reduce the size of the trigger transformer so that it would easily fit in a handheld enclosure. The main issue with transformers that should handle voltages so high is that it's very difficult to prevent internal arcing. A common method is to wind the transformer in sections and to separate each section with a piece of non-conductive material. And this is exactly how the pulse transformers we looked at earlier are made. This method can be very effective, but the part needs to be turned on a lathe, which I definitely don't have. I tried 3D printing it, but of course, due to the printing imperfections, it definitely didn't stand a chance of insulating 150 kilovolt. Another way was to wind a few rows separated by an insulator, but like before, it didn't work out too well. I settled on a much simpler solution, which was to simply use much thinner wire. That way, I could wind the necessary number of turns on a much shorter piece of PVC. Of course, a thinner wire means a higher resistance, which means a lot more losses in heat, but this is the best I can do for now. I could have instead reduced the number of turns on the primary, but that would also significantly reduce the efficiency. Like we saw earlier, this will need to be potted in epoxy to insulate the two coils. So this technique is really helpful, but it's definitely not a miracle insulator, as the transformer still needs decent insulation to begin with. Okay, now that I had my schematic, it was time to create a PCB. For this, I'll be using Easy EDA, which is a free PCB design software. I had these PCBs manufactured through JLC PCB's SMT service, who have kindly sponsored this video. JLC PCB is an online service that can manufacture custom PCBs at very low prices. Their assembly service allows you to design a PCB with tiny SMT components, and they will solder the components for you. No hassle at all. I've used their service on multiple projects in the past and have always, quite frankly, been blown away by the quality of their boards. For more info, check out the links in the video description. And here they are. You'll notice I have a bunch of extra SMT components and pads on the board. If you stick around to the end of the video, I'll explain what these were originally for and why I definitely didn't end up using them. The power traces on their own would have a hard time handling 13 amps, so I had to tin them. Now it was just a matter of designing a badass casing to hold all the components together. After sketching out a few ideas, keeping in consideration the dimensions of the components, I finally settled on this particular design as I quite liked its minimalistic yet intimidating appeal. After a few hours of modeling in SolidWorks, I printed out the two halves with my Anycubic i3 Mega 3D printer. I used PLA filament and 100% infill density for a nice solid enclosure. And finally, I could solder all the components on the PCB and assemble everything in the casing. And now is the part of the video where I show you all the f***ups and mistakes I made along the way. I originally encapsulated the entire high voltage circuitry in epoxy, just to insulate the entire thing. This created a few problems. Although epoxy is a great electrical insulator, it's also a great thermal insulator, which created some overheating issues. Also, if one component failed, the entire thing could just be chucked away, which ended up costing me a little bit of money. But the biggest fail was when I tried to use an Arduino Nano to control the stun gun. The issue is that I had to place it a few inches away from essentially an EMP device. You see, the problem here is that the primary coil of the trigger transformer emits so much electromagnetic radiation that it just fries any sensitive electronics near it. I tried adding a bunch of bypass and filtering caps, Zener diodes and inductances to try and filter nasty voltage spikes. I tried shielding the Nano with ferromagnetic material, but absolutely nothing worked.
Oh putain.
I think the main issue actually comes from the fact that I have a high frequency power trace running right next to the data lines of the Nano. This is definitely a big no-no, as it will induce a bunch of noise. But I'd already spent way too much time on this project, so I didn't really have time to fix it. But if anyone has any suggestions on how to properly shield the Nano, definitely let me know in the comment section. I'd love to read your ideas. And there you have it. So drop a like if you enjoyed the video and subscribe if you don't want to miss the crazy shit I'll be working on next. I would like to say a massive thank you to Electroboom for his cameo appearance. In fact, most of the high voltage physics I talked about in this video were learned from him. So if you'd like to dive deeper into the wondrous world of high voltage and you also want to see a man getting zapped from time to time, definitely check out his stuff. Thank you very much for watching, stay safe, and I will see you next time.